Okay, everyone. So here is your video lesson of inverse functions. We're going to only probably get through about half of the notes today, and then we'll finish up the second half and hopefully clear up any questions that we have from today, next class on Wednesday. So if you watch the preview video, you will hopefully remember that an inverse is an opposite or the undoing of something. When we talk about inverses with functions or relations, what we really mean is that we're swapping our x and y values. And so if we're given the relation, which is just a set of ordered pairs, and they ask us to find the inverse of it, it is as simple as, oops, swapping the placement of our x and y's in each of our points. So negative 5, 2 would become 2, negative 5 in the inverse. 4, 7 would become 7, 4. 11, 4 would become 4, 11. And 5, negative 1 would become negative 1, 5. And then this is just kind of a throwback. If you remember the beginning of the year, we talked about how we can determine if a relation was also a function. And it was based on the definition of for every x value, there could only be one y value, or if we were looking at the graph, that would mean it would pass the vertical line test. So if we were to scan a vertical line across our graph, it would only touch our our graph in one place at a time. So since we don't have a graph, we're going to use the first definition, which is to make sure that for every x, it is assigned to only one y value. Or another way to think about that in terms of ordered pairs is making sure that there are no repeated x values that would be or could potentially be assigned to two different y values. And in this case, we have no repeated x's, so for sure this relation is a function. Oh, actually, and I should have used this one. The inverse is definitely a function. That's what I was looking at here. 1, 2, 7, 4, and negative 1. There are no repeated x's, but the original is also a function because, again, there are no repeated x values. Negative 3, negative 5, 4, 11, and 5. So number 2 is just another example just like number 1. So I would like you guys to pause the video and give it a try, and then I will you can unpause it and then see how you did. So again, to find the inverse, all we do is we swap our x and y values, which in this case were written in a table. And when we compare to see if the relation is a function, again, we want to make sure that for every x, there's only one y value. And we have no repeated x's, so it is not possible for any of them to be assigned to another y. So this is a function. And the same thing with the inverse. The inverse is also a function. Okay. So those are two very, very basic inverse problems. We're going to get a little bit more complex when our function is now not just a set of ordered pairs or individual points on a graph, but an actual continuous function like a line or a quadratic, which makes a parabola, a square root graph. We have a whole bunch of function families. So in this case, when we actually are given a continuous function, like this is a line, to find the inverse, we're going to follow these 4 steps. So I'm going to do number 3 for you guys, and then I'd like you guys to try number 4 kind of the same way you did number 2, where you pause the video and try it on your own, following the same steps, and then unpause. So the first thing we're going to do is we're going to replace any function notation with a y, and then we're going to swap our x and y values. We said that that is what makes something an inverse of itself, is when you can swap the x and y values. And then we resolve for y. So I just put my y back on the left side where I like it. And then I replace that y again with function inverse notation. Okay, so that is how we find algebraically the inverse of a function in 4 easy steps. You're going to do the same thing with number 4. So I'd like you to pause the video here, give it a try, and then see how you did. Okay, so when we followed the same steps, we replace the f of x with a y, we swap our x and y value, and then we resolve for our y. So in this case, we had to subtract 2 from both sides, which gave us x minus 2. And then to undo the 1/3 in front of the y, we multiplied both sides by 3, making sure that we apply distributive property on the left side, which gives us 3x minus 6 equals y, and then we just rewrite it with our function inverse notation. And I can circle that one. Go and do that. Okay. All right, so moving on. 5 and 6 are very, very, very important problems, and I'd like you to maybe highlight them in some way. These are both quadratic functions. We can tell because they are second degree functions, meaning their biggest exponent on a variable is a 2. Now, what makes quadratic functions so difficult when we talk about inverses is that quadratic functions are not one-to-one functions. So they are functions, they pass the vertical line test, but what they fail is the horizontal line test, which is exactly the same thing as the vertical line test, except we're going to scan a horizontal line across the graph, and the horizontal line would have to touch the line in only one place at a time, or the horizontal line should only touch the graph in one place at a time for it to be a one-to-one function. But a parabola, which is a U-shaped graph, would definitely touch a horizontal line in more than one place at a time. So if I were to scan a horizontal line across a graph of a parabola, which is what quadratics make, we would end up touching in 2 places at a time, which makes it not one-to-one. So when this happens, the only way that we have for finding the inverse of it is to restrict the domain. So what I'm going to do is I'm going to bring up the actual graph of x minus 3 squared minus 4 in Desmos so you can see how to restrict the domain. Oh, sorry. Okay, so I've just switched over to our Canvas page real quickly because I wanted to take a minute to show you how to get to the Desmos graphing calculator. So along the left side of any page within the Advanced Math Canvas page, you can click on the Desmos graphing calculator and it'll pop up for you. And to type, you're going to want to just pop up this little keyboard button. And our function is, I believe, x minus 3 squared. Was it minus 4? I think it was. Let me just double check. Yes. Okay. So we can see clearly that it's not a one-to-one function, but in order to restrict the domain, I need to make it a one-to-one function, meaning it's got a left side and a right side that are symmetric. I always want to take the right side, or what will be the positive side, anytime I restrict the domain. So I only want, if I'm looking here, there's my vertex, that's where my dividing line between my left and my right side. I only want the right side of my domain, or in other words, I only want the x's. So I'm going to bring up my little brace, which is what makes x's greater than or equal to 3, and that's what indicates domain. So if you remember in the marble slides activity, the domain is what helps us figure out where our graph starts and stops. Okay. So I'm just going to zoom out a little bit so you can see more of it. But anyway, that is what we're looking for, just the right side of the graph. Okay, so I'm going to go back to PowerPoint. Okay, so we know that we have to restrict the domain, and that's the, oops, sometimes it doesn't recognize that this is a pen. Okay, so the first thing we're going to do is we're going to restrict the domain with the domain that we found from Desmos, which is x is greater than or equal to 3. And now we're going to follow exactly the same steps that we did before. We're going to replace our f of x with y. We're going to swap our x and y's. And then we're going to resolve for y. So add 4 to both sides. X plus 4 equals y minus 3 squared. So at this point, before I can even get to this y, I need to get rid of the parentheses, which are there because I'm squaring this whole term. So to undo that, I'm going to take the square root. So that leaves me with the square root of x plus 4 equals y minus 3. And now my last step would be to add 3 to get the y by itself. So now I'm just going to rewrite my y on the left. X plus 4 is inside the radical, but because I took the square root before I added 3, the plus 3 goes outside the radical. And it's very, very important that we make sure it's really clear what's inside and what's outside because it makes a big difference in terms of what our graph will do. So be very mindful of that. Okay. So the first thing we did was restricted our domain, and then we found our inverse is the square root of x plus 4 inside the radical and then plus 3 outside. Okay, so I'm just going to show you guys real quickly in Desmos. Here we are back in Desmos. I'm going to type in the equation of what I believe is my inverse, which is x plus 4 inside the radical and then plus 3 outside the radical. And it is graphed in blue. And the last thing I'm going to type in is the graph of y equals x because we learned in the preview lesson that the graph of a function and its inverse are always the reflection across the line y equals x. So we can see that the red and the blue are definitely reflections of each other across this line y equals x in green. That would not have been the case if we had not restricted our domain on our quadratic. So remember that that's a very important step when you have a non-one-to-one function. So which functions will be non-one-to-one where we'll have to pay attention to this? Quadratics are going to be your most common. So any graph that has left-right symmetry like quadratics will have that. And functions that have left-right symmetry are all even degreed functions. So 4th degree, 6th degree, 8th degree, although we won't see, beyond 4th degree very often. The one other type of function that that is not one-to-one would be an absolute value function. So those would also have to be restricted in the domain. And again, it's as easy as looking at the graph in Desmos and then only restricting the right side of the graph so that you eliminate the left side. Okay, so what I'd like for you guys to do is to try, we're going to go back to the notes, and I'd like you guys to try, and I went to the wrong spot. Sorry, let's go back through. Pause the video and try number 5 and then unpause it and see how you did. So again, we had a quadratic here. So we had to restrict the domain, which you can find by looking at your graph and only taking the x's that are greater than or equal to the vertex, the x coordinate of the vertex of your graph, so that it's only the right side of your graph. Once you've done that, then you just replace your f of x with a y, swap your x and y's, resolve for your y. So we subtracted 1, and then we took the square root of both sides. So the inverse of f of x is the square root of x minus 1, as long as we restricted our domain from the beginning over here with x's greater than or equal to 0. Okay, so let's move on to another type of example. These are both cubic functions, and cubic functions are one-to-one. They are not an even degreed function, so we can find the inverse without having to restrict the domain. So just to save some time, I have worked them out following the same procedure that we've been doing, which is to replace the f of x with a y, swap the x and y, and then resolve